So I'm Michail, or Michalis. I'm from Greece, but I'm a PhD student at Stockholm University now. I work with Gunilla, and the topic of my studies is basically the exchange of air between the mid-latitudes and the Arctic, and specifically how the air masses are transforming on their way in and out of the Arctic, especially on their way in when we have these warm air intrusions. So this is what my presentation is going to be about. It's going to be about the warm air intrusions that we had, that the MOSAiC expedition observed during April 2020, and I'm going to give you a demonstration on how you can use the AOSCM, which is the Atmosphere and Ocean single column model, to simulate this kind of meridional transport and what the limitations are and also what the benefits are in such an approach. So you can use the AOSCM basically in two frameworks. One is the Eulerian and the other one is the Lagrangian. And there are different things to consider in each framework, but the structure of the model is the same. You have an atmospheric column that is on top of an ocean column, and then there's sea ice in between when we're at locations near the poles. And these are treated with different models, OpenIFS for the atmosphere, NEMO for the ocean, and then LIM3 for the sea ice. And these are all coupled together with OASIS, and you can learn more about this configuration in the paper by Harten et al. 2018. But the important thing to know about this configuration is that it's a single column model that resolves the physics on the vertical, but still needs some information about the large scale circulation that comes in the form of advective tendencies that bring in moisture and heat and momentum into the column. And that's how the model is aware of the large scale flow and has some kind of interaction with the ambient environment. At the surface, we have the exchange of a lot of information because the ocean needs all these fluxes, the solar and non-solar fluxes from the atmosphere, and also how the temperature is sensitive to those non-solar fluxes. Momentum fluxes and sources and sinks of water through precipitation and evaporation, and also the sea ice properties, and gives back to the atmosphere an updated value for the sea surface temperature, and also some aggregated mean values of the ice parameters. So we have sea ice concentration and the thicknesses of sea ice and snow, and the temperature, and also the rate of change for the ice thickness. So we can take all that and apply it on a real case scenario, that is the TOP case, the 10-day period between 12 and 22, let's say, of April in 2020. We can position our column on the location of polar stern, so we can have this direct comparison between observations and simulations. And you can see this is the star represents the location of polar stern. You can see the atmospheric rivers reaching that location, and you can see what they are doing to the temperature at the surface. The gray line is the observations, and then the blue line is what we're simulating with the AOSCM. And those sudden changes in the simulated curve are because this is not a full-length, uninterrupted simulation. These are tiny, smaller simulations that are stitched together. So what I did is I initialized simulations on each day, and then I took the second days of each simulation and stitched them together to create this time series for the entire period. And the reason I did that is because I needed to give some spin-up time for the model, and also to not allow it to drift too much from the ERA 5 reality, at least, that I used to initialize it and force it. And also to be able to use this sea ice information that we have from the MOSAiC observations and to give a more realistic sea ice surface for the atmospheric column to respond to more frequently, so I could update it daily. So we can see the first results here. There's a lot of results. I don't think we're going to have time to look at all of them, but there's liquid water path and radiative fluxes and turbulent fluxes, the surface energy budget, and then temperature and velocity near the surface, and then, of course, at the right, all the sea ice properties and their evolution, albedo, ice fraction, and thickness of sea ice and snow. So I think the main takeaway of this slide is that the AOSCM is actually doing a very good job simulating this entire period, but it's not always doing a great job. There are still some areas of concern, let's say, like when we have these compensating errors that other people have mentioned too, and we are not entirely sure why and how they arise and how to treat them. But also we have some periods where the model is consistently underperforming, and these are these blue shaded periods where in observations we see that the surface is supposed to be cooling, but this is not what we're seeing in our model simulations. The model doesn't lose as much energy as it's supposed to, and that is more apparent here where we have these accumulated energy time series by integrating in time the fluxes, and then in the total row you can see that in the blue boxes we have more energy and excess energy in our simulations, and you can see also why if you look at the sensible heat, that it's the sensible heat that it doesn't let the surface to cool. We have a lot more than we're supposed to, and that may be linked to the model's inability to actually represent these intricate boundary layer structures in the Arctic boundary layer. So we're left with this warm bias when the warm air masses leave the column, and these air biases can be found near the surface, but also up to 1 kilometer above the surface on the days after the warm air intrusions. So this is a first look on what the Eulerian simulations look like, and we have areas and periods of interest that we're planning to look further into, but now I would like to show you what our Lagrangian simulations look like and how we worked on them to set them up and what the first results show. So what do you need to set up a Lagrangian simulation? First of all, you need a trajectory, and you can have a lot of those using different tools, but what we used is Lagranto, and we initialized trajectories at different pressure levels from 950 to 500 hectopascal on a circle around polar stern. And these trajectories that you get to see now are the trajectories at each level that are the closest to observational stations. So we can have at least 3 points of verification downwind along our trajectory, so we can monitor how our simulations are actually doing. Another interesting feature about these trajectories is that they seem to be lining up on top of each other. So they're very close in space and time, with the exception of the 950 hectopascal, which is the one that is further to the east. And they have similar lengths, they're close in space, and that gives us some motivation and some confidence to look at this flow situation like it's parcels that are moving on top of each other, and it's a single column that is being advected along a singular common trajectory. So we can use the AOSCM to simulate that, and we can turn advection off, quote unquote, and by that I mean turn the advective tendencies off to zero, and then simulate advection by basically changing only the surface properties and have the atmospheric column respond to those changes. We still have to have some information about the large scale circulation, so we have to nudge the profiles at least of the wind speeds and at least from one altitude and over to have this information imported into our simulations. And we also use a pressure gradient forcing by having the geostrophic wind profiles. But the last thing that we have to be aware of, that we have to check, is that the model can actually understand that the surface, that it's actually moving, and that is easier in some situations when you're over sea and you can have a temporarily varying SST. So by having a cooling surface, you can actually emulate a poleward advection. But this is not the case when you have changing, you're advecting over different types of surfaces, because the model doesn't sense that the land fraction or the sea ice fraction or even the latitude is changing, so that you're having a different shortwave input. So what we had to do is break up these trajectories into smaller sub-trajectories that correspond to different surface properties. So we have a leg over sea, a leg over sea ice before the land, over land, and then after the sea ice after the land. What I'm going to show here is going to exclude the land so that we can have a more simplified view on it. So we have a long sea leg, sea ice leg south of Svalbard, and then a sea ice leg north of Svalbard, where we can actually use the measurements from MOSAiC to initialize. And these are the results of these trajectories. The cross-sections on the right are the AOSCM, and on the left is the ERA 5 across, along those trajectories. So right away you can see that the simulations have more moisture in the boundary layer than they're supposed to, according to the ERA 5 always. And that extra moisture is resulting into more cloud formation. And this cloud formation in return is resulting to more heat in the surface that's leading to a warm bias further downstream. And what is even more annoying is what's happening with the winds is that when we're not nudging them to the reference profiles, we're getting these inertial oscillations that you're getting in single column models when you don't have advection and you're trying to force with pressure gradient. So this is something that we're still trying to figure out how it's affecting our results and how to actually mend and mitigate. Regarding the surface, these are the fluxes, turbulent fluxes on the right and the left. I think tell the same story in our simulations and the ERA 5 trajectories. What's messing everything up is the extra liquid water path on the bottom that gives us zero radiative, long wave radiative fluxes, and then a lot less shortwave radiative fluxes. But if we, having said all that, if we compare where we started and where we ended up, we can see that we started from something that looks realistic and we're ending up at something that also looks realistic, and there's something going wrong in between. So this is what we're going to focus to actually have control over the processes and understanding of them and what the model is doing. Do I have time to summarize? Okay. Okay. So the AOSCM was running in Eulerian mode, and that was gave us a more accurate description of the 10-day period of the TOP case. But we still have some warm biases. The Lagrangian simulations weren't as successful in their accuracy, but are still very informative and are still a nice way to simulate the air mass transformation and the process that goes, the processes that lead up to it. And I wanted to also highlight the need for observations along the trajectory and how we can get that from aircraft expeditions like the AC-3 expedition that we had this spring, that the scope was to actually follow the air masses and measure them along the trajectories. So I think I can close with that. Thank you.
Thanks very much. I think we have time for one question.
Could you go back to your first slide where you showed the comparison between the, just wanted a confirmation of something actually. First slide between, yeah, there.
Oh, wait.
So what do you mean by CMEMS when you have ice fraction and ice thickness?
Ice fraction and ice thickness?
And
yeah.
Yeah.
CMEMS is what is the reanalysis, what the reanalysis is showing at that location.
So the ocean reanalysis.
Yes.
Okay.
Oh, me?
Okay.
Yeah. Okay, sorry.
And,
Yeah.
and that applies to the thickness as well then, too.
Yes, exactly.
But wouldn't there have been some MOSAiC observations of at least thickness?
The observations, the thick line is MOSAiC. And Siemens analysis, yeah. It could be phrased better, yeah.
Okay, thank you.
Perfect. Thanks very much.
Thank you.